Okay, so in this lecture I'm going to be discussing a concept known as implicit differentiation. And so implicit differentiation is basically just something which we actually saw when we were discussing derivatives of inverse functions, where you take the derivative of both sides of an equation. Let's try to understand why this is called implicit differentiation. In order to do that, we need to understand what's an explicit function and what's an implicit function. So a function is explicit if it has a form y equals f of x. So in other words, we've isolated the y, have it all by itself, and it just equals some function of x. So basically, just about everything we've seen in the class so far has been an explicit function. An implicit function y is not isolated. So, for example, we might have something like y cubed plus 3x squared equals 17. And this is an implicit function because the y is mixed together with several other things. Now we could make this an explicit function by rearranging it. If we move the 3x squared to the other side and take the cube root, then we can get y equals cube root 17 minus 3x squared. However, that's not always possible. So as another example, if we have y cubed plus 3xy equals 17, very little change, just added one more y to the equation. Now it's extremely difficult to solve for y as an explicit formula, so we really have to leave this as an implicit formula. But still, if you give me a value of x, I'll get some equation that I can then solve for y, maybe by graphing it and looking at where the zeros are, right? It'll be some cubic equation in y. So still, given an x, I get a y value. However, it's not quite as straightforward as when we have an explicit formula. We have to do some additional work after given the x value to solve for what y should be. So let's look at another example, which is the equation x squared plus y squared equals 1. So as you probably know by this point, this is an equation for a unit circle. And we can try to solve this and make it an explicit equation. So we could write y equals square root 1 minus x squared, or negative square root 1 minus x squared. So if we have the positive square root, we get the top half of the circle. If we take the negative square root, we get the bottom half of the circle. But if we really want to work with the full circle, it's inconvenient to have to split up into two equations like this. So this is a case where it's really more convenient to work with an implicit formula, because now we just have one single equation to work with. And so let's say, for example, that we want to find the tangent line to the circle at some point, x comma y. Maybe let me put bars overhead to distinguish it from the x and y that appear as variables in the equation. So, right, these are just fixed numbers that would be given to you. So on this circle, notice that it's important, when we were finding tangent lines before, I just gave you an x coordinate, and then you could go and find the tangent line by figuring out the corresponding y coordinate. Here I have to give you both an x and a y, because for any x coordinate, there's two possible y values, right? This thing is not a function. So in order to know which tangent line we're talking about, I need to give you both values here. So if we wanted to find the equation for this tangent line, we need to know what is the value of y prime, right? So y prime should be the slope of the tangent line. However, if we do this, then we have two different equations for y, so we'd have to figure out which one is appropriate to use depending on the point. That's a bit annoying because I haven't been told, for example, whether y bar is positive or negative. So if I want a general formula that's correct regardless of whether y bar is positive or negative, this is really inconvenient because I don't know which formula to use. So that's why we want to work with this implicit equation here, because it's always valid, regardless of the values of x bar and y bar. So the question is then, how can we get y prime from this equation? Well, we can differentiate both sides of the equation, right? We want to know something about the derivative, so we take a derivative and see what happens. Now the derivative of the left-hand side is 2x plus 2y times y prime. So we get the 2y because the derivative of y squared gives us 2y by the power rule. But then y is itself a function of x. There's something inside the squared which is itself a function, and therefore by the chain rule we have to get the derivative of the inside function, which is this y prime. And this all should be equal to 0. So now you see, by doing this implicit differentiation, where we differentiate both sides of an implicit equation, we get a new equation which has y prime in it. And we can proceed to solve for y prime and get that it's negative x divided by y. And this is valid regardless of whether we have positive x and y values, negative x and y values, or some combination of that. So if we want to find the equation for the tangent line, we'll have y equals the slope, which is negative x bar over y bar, times x minus x bar plus y bar. So this is the point slope formula. So this would be the tangent line for the circle, and if I give you two coordinates, for example, maybe x bar is 1, y bar is, or wait, it's a unit circle, so I can't go that far out. So let's say x bar is like square root 2 over 2, y bar is square root 2 over 2, so it's somewhere up here. Then I just have to plug those values in for x bar and y bar in this equation to get the tangent line. And then if I pick another value down here, I still plug into this equation. If I'd use the explicit form, then I would get one tangent line equation for this one up here, and I could plug those values in to get that. But then if I wanted the tangent line down here, I'd have to use the other equation. So that's why this method is much better, because we only have one equation we have to deal with. Alright, so that's basically the simplest example we can have. Let's look at another example in detail. So this is the folium of Descartes. So the equation is x cubed plus y cubed minus 2xy equals 0. So the graph of this function ends up looking something like this. So again, based on the fact that this thing is not actually a function, we can see that it's probably not going to be so easy to write it as an explicit equation. And indeed, I think you would be very hard-pressed to solve for y explicitly in this example. So let's see if we can calculate the value of y prime, even though we cannot solve for y. So we use implicit differentiation, take the derivative of both sides. If we simplify this, we get 3x squared plus 3y squared times y prime. Again, we get this extra y prime by the chain rule. Now this term, we have x times y. Those are both functions of x. We really have a product rule going on here. So the first function is the 2x, the second function is the y. So derivative of the first function gives us negative 2 times the second function, minus derivative of the second function is just y prime times 2x. And this all is equal to 0. So now if we isolate the y prime, then we'll get y prime is equal to negative 3x squared plus 2y divided by 3y squared minus 2x. So I've skipped some steps here, I guess, but this is just some rearrangement of this equation. You move all the terms without y prime to the right-hand side, then you factor out a y prime and divide by what's left, and that's all that happened here. So if we wanted to find the tangent line at some point, then we would use this formula for y prime to find the slope. So some particular interesting things we can look for is when is the slope equal to 0, or when is there a horizontal tangent line. So in order for y prime to be equal to 0, if a fraction is equal to 0, it must be the case the numerator is equal to 0. So we'll have negative 3x squared plus 2y equals 0. We can solve for y and get that y is equal to 3x squared divided by 2. Now, unfortunately, not all of these values of x and y are going to be points where there's actually a horizontal tangent line. So if you think about this, this is some parabola that would come in something like this. It's only going to actually touch this curve at a few points. But if we want to know where is there a horizontal tangent line, we're only interested in the points that lie on this curve here. So we need to figure out what points does this parabola, where the slope is potentially 0, actually intersect the curve that we're interested in. So in order to do that, we need to see if y is equal to 3x squared divided by 2, what is the value of x so that this equation is satisfied. So let's plug in the value of y to this original equation for the graph. We get x cubed plus 3x squared over 2 cubed minus 2x times 3x squared over 2 should be equal to 0. And if we rearrange this, we get x cubed times negative 2 plus 27 over 8x cubed should be equal to 0. And this tells us that either x equals 0 or x equals 2/3 cube root of 2, if my calculations are correct. You have to do a bit of arithmetic here, but basically I'm just saying either this is 0 or this is 0, and that leads to these two possibilities. So if x is equal to 0, then we can see from this equation up here, the only possibility is that y is also equal to 0. But then our derivative becomes a bit strange because we're now dividing by 0. So let's revisit this case of x equals 0 and y equals 0 in a moment, and think about this one. So if x is equal to 2/3 times this, then y is equal to 3x squared divided by 2. So this is equal to 2/3 cube root of 4. So at this point, when x is 2/3 cube root 2, y is 2/3 cube root 4, it gives us a derivative of 0. So that means we have a horizontal tangent line. That will correspond to this point on the folium of Descartes. Now what about 0, 0? That would be right here at the origin. Notice that this is a point where the curve intersects itself. So yes, if we're coming in along this top band, we are on this piece here, and it looks like the tangent line should have a slope of 0. Then when we go around, we intersect our curve again. Now it looks like the tangent line is vertical coming in from this piece. So in that case, the slope certainly would not be 0. It would be like an infinite slope. So because the function intersects itself here, there's actually no well-defined tangent line. So we have to throw out this point, x equals 0 and y equals 0. There is not a horizontal tangent line there because the tangent line is not well-defined. Okay, so similarly, actually let me stick on this for a moment. So if we wanted to find where there's a vertical tangent line, then we'd want to know where is y prime undefined, or where are we dividing by 0. And so in that case, you would take the denominator function, set that equal to 0, and very similarly, you would find 1 point corresponding to the one over here, and you'd also get 0, 0 over again, or 0, 0 again, but you'd have to throw that out because there's not a well-defined tangent there. Okay, so let's see one more example of what we can do with implicit differentiation. So we can actually find derivatives of some rather interesting functions. So let's start by finding the derivative of x to the power x. So this thing looks a bit intimidating. Certainly if you use the definition of derivative, this is not going to be very useful. And the derivative rules we know don't really apply because it's not a power function because the base, or sorry, it's not a power function because the exponent is a variable. It's also not an exponential function because the base is a variable. So none of the rules we know will help us. So how can we approach this problem? Well, let's start by writing y equals x to the power x. Now, we want to find y prime. The real reason why we're having trouble is because there's an x in both the base and the exponent. So let's try to get rid of the x in the exponent. The way to do that is to take logs of both sides. So we'll get something which looks like this. Now from here, we can do implicit differentiation, and now we do know how to differentiate everything using the rules that we've already learned. So if we take the derivative of the left-hand side, then we'll get 1 over y times, by the chain rule, the derivative of the inside function, which gives us a y prime. And this is equal to, we have to use a product rule on this piece, so we'll get derivative of the first function times the second is log of x, plus derivative of the second function times the first, that's 1 over x times x, which gives us 1. So if we rearrange, we'll see y prime is equal to y times 1 plus log of x. Now, in this case, we didn't start with an implicit function, we started with an explicit one. We just wanted to find the derivative of x to the y equals x to the power x. So it would be nice if our final answer was not in an implicit form, if we want our final answer to be in an explicit form. So the way we can do that is to recall that y is equal to x to the power x. So if we plug that in down here, we get something like this for our final answer. So this is an example where implicit differentiation was very useful for actually calculating the derivative of a function that was already given to us explicitly. So sometimes implicit equations can actually be more helpful to us. So that's everything I wanted to say about implicit differentiation, I think. It's a very useful technique, and it really doesn't require too much new abilities beyond what we've already covered in the class, basically just taking derivatives of functions, but we're doing derivatives of functions in a new way that allows us to do a lot more things. I mean, for example, something like this, I mean, this thing isn't even a function, it's some really complicated curve, and yet we're still able to do things like find slopes of tangent lines and so on. So that's sort of what makes implicit differentiation really powerful.